In this video, we will learn how to carry out multi-load topology optimization. To begin with, let's start with a model. We will use the multi-load test part for as an example. And one thing you'll notice is that the ParetoWin now suggests that perhaps this model is in inches. STL files, as we all know, is unitless, and depending on the dimensions of the part, ParetoWin suggests that the dimensions really should be inches, not meters. And it's up to the user to make sure that the right units are used. In fact, for this particular model, the STL file was saved in inches, so we will change this to the inch dimension, and all that is reflected on the left-hand side. For the material, we will use AL1060, apply, and that's reflected here. For the boundary conditions, we will restrain these two faces, hold the control key, select the second face, pick XYZ fixed, that's fixed in all the three directions, and we apply. And we'll apply a vertical force that's in the negative Y direction, a force of 8,000 pounds because we're an inch-pound IPS system, and we apply a load. Of course, one can now carry out FEA and topology optimization and so on, but instead what we'll now do is we'll apply multiple loads. So this is one load scenario. Often in design, you'll have multiple load scenario. To change the load scenario, we will use the load set feature. When we increase the load set, you'll notice that the restraints remain as they are, but the loads have vanished. In other words, now we can now apply a different load on this face, for example, and we'll do that right here. We'll apply a diagonal force you need to select the face, of course, and apply the force, and there we are. So what we have now is a two-load scenario. The first load is a vertical force, the second load is a diagonal force. Now what we're looking for is a single topology that can handle both loads, satisfy the stress constraints, satisfy the design constraints. So that's called a multi-load topology optimization. And first what we'll do is we will carry out an FEA to make sure our load sets have been captured, and you can scroll through different load sets. The first load set is a vertical force. We will use a medium quality mesh and carry out a static FEA. And this should reflect the vertical load force, as you can tell, and the stresses are all captured here, and we're still a little bit further away from the yield stress for this particular load set. Similarly, we can do a second load set and carry out an FEA. And once again, the finite element results should reflect that particular load set. Next, we'll move on to topology optimization. A few of the features we discussed previously are the desired volume fraction, and we'll set that to 0.01, which is remove as much material as possible, and the stress constraints are the yield stress. We'll leave that as it is, and the keep fixed faces, we'll select that because we want to retain material around these two holes. And the draw direction, we learned that in the previous video. We'll set that to the Z direction, which is the thickness direction, and we also like symmetry. So all these features we have studied so far. The new feature we will study are these two, use all loads or use a specific load. What this allows you to do is it allows you to explore different topology optimization results for different load conditions. If you unselect this, then you can use the different loads here to get different topology optimization results for each of the loads. So we'll set it to load 0 and we'll search for the optimal topology for just the load 0. The load 1 will not be active because you've unselected this. And let's go ahead and optimize. And we'll wait for the results to complete. The optimization is complete. And this is the final result where indeed one can observe that the yield stress is the maximum stress is very close to the yield stress. And we have hit a volume fraction of 0.23 for load 0. Now let's optimize the topology just for load 1. And again, with this unselected, let's move to load 1 and optimize the topology. The optimization is complete, and you should notice that the topology is very, very different from the previous topology. In fact, the topology is simply a straight bar because the force that we applied was diagonal going through the lower hole. And this topology is in fact different and is once again stress constrained. The next thing we'll do is optimize the topology with respect to both loads. So once you select this, then all the loads that we applied, in this case we applied 2 loads, both of these loads will be considered and you'll arrive at one single topology that's optimal with respect to both of these load conditions. So let's go ahead and optimize. And this of course will take a bit longer because now the optimization has to run through both sets of FEA constantly to find the final topology. The optimization is in fact complete now, and you'll see that it has features from both the loads. It's optimal with respect to both loads. It satisfies the stress constraint and the design constraints. And this concludes the video on multi-load topology optimization.